ever-changing seismic provisions of our building codes. We started yesterday by pointing out, and I think it is necessary to repeat this today in case some of you did not attend yesterday, that the structural provisions of our code, uh, first of all legal codes are now essentially all legal codes are now based on the IBC. And the structural provisions of the IBC are taken from ASCE 7. All of you know this. So the structural provisions of the IBC undergo big changes only when the referenced ASCE 7 edition changes. 2006 and 2009 IBC were based on or they adopted ASCE 705. That changed with 2012 IBC, 2012 and 2015 IBC adopted ASCE 710. So when we went from 2009 to 2012 IBC, and the reference standard went from ASCE 705 to ASCE 710, we had big changes in structural provisions. Same thing happens when we go from 2015 to 2018 IBC, which is about to happen. We will go from ASCE 710 as the reference standard to ASCE 716 as the reference standard, and that also involves big changes that some of which I will point out to you in this seminar. So I did mention to you that today's seminar is about seismic design, and after thinking that these things are a challenge to put together, I thought the starting point should be, and that's where I would start, the concept of the response spectrum. Design ground motion at a site and response spectrum. The instruments called strong motion accelerographs are deployed at many locations around the globe. When the earth moves in an earthquake anywhere around the globe, many of these instruments would record the ground acceleration as a function of time in 3 mutually perpendicular directions. So ground accelerations are recorded in 2 orthogonal horizontal directions and in the vertical direction. So 3 components, if you like, of ground acceleration are recorded as a function of time. These plots are called accelerographs. The instrument is accelegraph. The plot is accelerogram. The strong motion part, why we call them strong motion accelerographs, is that these instruments are not triggered until the peak ground acceleration exceeds a certain threshold value that is preset, and the instrument shut off when the peak ground accelerations go below that threshold. Okay? So it's only the strong motion part that is recorded. Now agencies like USGS who do this kind of recording or collect this type of recording, they would routinely integrate the accelerations with respect to time, and that integration would give us ground velocities as a function of time, which is the middle plot. The top plot is the recorded accelerogram of the north-south component of the 1940 Imperial Valley earthquake as recorded at the El Centro station. we go back to that old earthquake because it is one of the oldest strong motion records and has been used in many, many, many analytical studies around the world. And it is, I could obviously show you another, but anyway, this is probably the most well-known record there is. Now the ground velocities that are obtained by integration of the acceleration record are integrated one more time with respect to time, yielding ground displacements, which you see in the bottom plot as a function of